Now in this video we shall consider the difference method of estimation. So we have considered the ratio of the two sample means and proposed ratio estimator. We consider the product of two sample means y bar and x bar. We propose product estimator. So in a ratio method of estimation which makes use of the auxiliary information, and it was seen that the ratio estimator provides an efficient estimator of the population mean if the regression of y on x, a regression of y on x, that is study variable and the auxiliary variable, is linear and the regression line passes through origin. A regression line passes through origin. It happens frequently that even though the regression of y on x is linear, but the regression line do not pass through origin, does not pass through origin. So under such conditions, it is more appropriate to use the difference method of estimation than the ratio method. We consider a finite population of n units, and to estimate the population mean y bar, we select a sample of size n by using SR-SWOR scheme and observe both study variable and the auxiliary variable and calculate the x bar and y bar for this sample. So Hoorage and Meadow in 1953 they suggested this difference estimator, and the difference estimator for estimating the population mean is given by y d bar, that is equal to y bar minus beta 0 small x bar minus x bar, where beta 0 is a constant. Beta 0 is a constant. Now we can find expectation of y d bar, that is equal to expectation of y bar minus beta 0 expectation of small x bar minus capital X bar. So that is equal to expectation of y bar, that is equal to capital Y bar. So for all values of beta 0, for all values of beta 0, for all values of beta 0, the difference estimator y d bar gives an unbiased estimator of the population mean y bar. Now we find the variance of the difference estimator equal to expectation of y d bar minus y bar whole square, that is equal to expectation of y bar minus y bar y d bar, that is y bar plus beta 0 x bar minus x bar minus beta 0 x bar minus x bar minus y bar whole square, that is equal to expectation of small y bar minus capital Y bar minus beta 0 small x bar minus capital X bar whole square. Now that is equal to expectation of small y bar minus capital Y bar whole square plus beta 0 square expectation of small x bar minus capital X bar whole square minus 2 beta 0 expectation of small y bar minus capital Y bar to small x bar minus capital X bar. So that is equal to 1 minus f by n, this will be sy square plus beta 0 square, this is sx square minus 2 beta 0, this is syx. So we get so this is the variance of the difference estimator where beta 0 is constant. Now in particular, if you take beta 0 equal to population ratio y bar by x bar, this variance becomes equal to variance of the usual ratio estimator. Now when beta 0 is the population ratio, the variance of the difference estimator becomes equal to the variance of the usual ratio estimator. Now in the difference estimator YD bar, we have YD bar equal to y bar minus beta 0 x bar minus x bar. This beta 0 is a constant. So the constant beta 0 may take different values, but we have to determine a value of beta 0 for which the variance of the difference estimator is more efficient. That means variance of the difference estimator is minimum, so that the difference estimator YD bar will be more efficient. So we have to minimize the variance of the difference estimator. That is, we have to minimize 1 minus f by n sy square plus beta 0 square sx square minus 2 beta 0 syx. By minimizing this with respect to beta 0, we get the minimum variance, and that will provide the value of beta 0 for which the difference estimator will be most efficient. So we differentiate variance of YD bar with respect to beta 0 and equate to 0, so that we get 2 beta 0 sx square minus 2 syx equal to 0. That implies beta 0 equal to syx by sx square, that is equal to beta yx, or simply we denote it as beta, that is the population regression coefficient between y on x, the population regression coefficient of y on x. So that means when beta 0 is equal to beta, that is the population regression coefficient of y on x, we get the minimum value of the variance of the difference estimator. So using this beta 0 equal to beta, now our difference estimator becomes YD bar, that is equal to y bar minus beta small x bar minus capital X bar. Beta is the population regression coefficient between y and x, and now this is the optimum value of beta 0 is beta. Now the minimum variance of the difference estimator is given by 1 minus f by n into sy square plus beta square sx square minus 2 beta syx. Now this is 1 minus f by n sy square plus beta square syx square by sx to the power 4 into sx square minus 2 beta syx by sx square. Beta is the population regression coefficient into syx. So that is equal to 1 minus f by n. This will be sy square minus this sx to the power 4 sx square. So this will be sx square. So this will be syx square by sx square. So this will be equal to 1 minus f by n sy square, taking common 1 minus syx square by sy square into sx square. Now rho is the population correlation coefficient between y and x, so rho will be equal to syx by sx. So this will be rho square. So variance of this minimum variance of the difference estimator is given by 1 minus f by n sy square to 1 minus rho square. Now if we compare the difference estimator with the simple mean estimator, that means we compare y d bar with y bar, compare it. Variance of y d bar, that is equal to 1 minus f by n minimum variance sy square 1 minus rho square, and variance of y bar equal to 1 minus f by n sy square. Now if we take variance of y bar minus variance of y d bar, so that will be equal to 1 minus f by n minus rho square, which is always less than 0. So this difference estimator in its minimum case is always preferable than the simple mean estimator. So here minimum case means we take beta, the population regression coefficient of y on x, in place of beta 0. But for any arbitrary value of beta 0, if we compare, this will be variance of y d bar, that is equal to 1 minus f by n sy square plus beta 0 square sx square minus 2 beta 0 syx, and variance of y bar, that is equal to 1 minus f by n sy square. Now if we subtract variance of y d bar from variance of y bar, this will be beta 0 sx square minus beta 0 sx square plus 2 beta 0 syx, so into 1 minus f by n. So that will be equal to 1 minus f by n beta 0 square sx square, taking common we get 2 beta minus beta 0. Beta is the regression coefficient between y and x, syx by sx square. Now therefore the difference estimator y d bar will be more efficient than the simple mean estimator if beta 0 into 2 beta minus beta 0, this is greater than 0. That means beta 0 lies between 0 to 2 beta. So the difference estimator will be more efficient than the simple mean estimator if this condition is satisfied. So from the above we have seen that beta 0, if beta 0 is close to beta, if beta 0 is close to beta, then the variance of the difference estimator yd bar will be close to its optimum variance. But if beta 0 differ substantially from beta, then the variance of the difference estimator will be sufficiently more than its optimum variance. Hence, it is necessary to investigate between the closeness between beta 0 and beta. That means how much beta 0 differ from beta. If beta 0 deviate from beta more, then the variance is not. Then if beta 0 is close to beta, then the variance of the difference estimator will be close to its minimum value. If their difference is more, then it will differ much from the optimum variance, and sometimes it may happen that its variance will increase to a very high amount, leading to a very less efficient difference estimator. So we investigate the how much beta 0 differ from beta, that is the population regression coefficient of y on x. So to measure the difference between beta 0 and beta on its variance, we assume beta 0 equal to beta plus d, where d is a small increment over beta. Now variance of the difference estimator, that will be 1 minus f by n, that will be sy square plus beta plus d square sx square minus 2 beta plus d syx. So that will be 1 minus f by n, this will be sy square plus beta square sx square minus 2 beta syx plus 2 beta d sx square plus d square sx square minus 2d syx. Now if we use beta equal to syx by sx square, that means population regression coefficient of y on x, this variance will be equal to 1 minus f by n, this will be sy square 1 minus rho square plus d square sx square. Now this is 1 minus f by n into sy square by 1 minus rho square. This is the optimum variance. Now this is the increase in variance due to the difference between beta 0 and beta. So when d equal to 0, that means beta 0 equal to beta, then variance of the difference estimator yd bar equal to 1 minus f by n sy square 1 minus rho square, which is the minimum variance. So now the variance of yd bar, that will be equal to into sy square 1 minus rho square, taking common, this will be 1 plus d square sx square by sy square into 1 minus rho square. So that is equal to 1 minus f by n sy square 1 minus rho square, this will be 1 plus delta square, where delta equal to d sx by sy root over of 1 minus rho square. Delta square equal to d square sx square by sy square into 1 minus rho square, that is equal to beta minus beta 0 whole square sx square by sy square into 1 minus rho square. So that is equal to beta minus beta 0 whole square into s x square by sy square into 1 by 1 minus rho square. So we have beta equal to rho sy by sx. So that implies rho by beta equal to sx by sy. So implies rho square by beta square equal to sx square by sy square. So now delta square is equal to, using this value here, we get delta square equal to beta minus beta 0 whole square into rho square by beta square into 1 by 1 minus rho square. So that is equal to rho square by 1 minus rho square into beta minus beta 0 by beta whole square. So that is equal to rho square by 1 minus rho square into 1 minus beta 0 by beta whole square. So thus delta square represents the increase in variance. This is increase in variance due to using a value beta 0 instead of using beta, the population regression coefficient of y on x. Thus delta square help us to investigate how beta 0 deviate from beta. Suppose we want the relative increase in the variance should be less than alpha %, which means that delta square less than alpha. So that implies rho square 1 minus beta 0 by beta square by 1 minus rho square less than alpha. So that implies rho square into 1 minus beta 0 by beta whole square less than alpha into 1 minus rho square. That implies 1 minus beta 0 by beta mod less than root over of alpha into 1 minus rho square by rho square. This we are writing equation 1. So now we want to achieve that the relative increase in the variance should be less than alpha %. Then we have to choose beta 0 such that the equation 1 will be satisfied. Now we can make a table showing how the value of delta for different values of alpha and rho. Now we can make a table. Here we can take a rho. This is alpha 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Here alpha we can take 0.05, 0.1. 5%, 1% we generally choose. So this will be 0.71, 0.51, 0.39, 0.30, 0.23, 0.17, and this will be 1.01, 0.72, 0.55, 0.42, 0.32, 0.24. So from the above table we can see that as the value of rho increases, the value of rho increases, the value of delta decreases for a fixed value of alpha. So generally the value of beta 0 is not known, and in the value of beta 0 we consider an estimate of beta 0 from the previous data if available, and in that case we can take the beta 0 we take estimate of beta, that the estimate of the population regression coefficient of y on x as the sample regression coefficient of y on x. The difference estimator yd bar reduces to y bar minus beta cap x bar minus x bar, that is y bar minus syx by sx square x bar minus x bar. So this estimator is called as the linear regression estimator, which we shall study in our next video. Thank you.